Nachman to give our quant talks today. He is a group leader for machine learning for fundamental physics at the Lawrence Berkeley National Laboratory. And in particular, he is a founding member of the Quantum Algorithms for High Energy Physics group. But don't get too scared about high energy physics. The techniques which he is developing is actually are far more general than just applying to high energy physics. And that should be interesting for people who are working on many body problems in statistical mechanics as well as quantum field theory. So as a matter of his background, Benjamin did his bachelor's from Cornell University in 2012. Then he went to Cambridge to do master's with a Churchill scholarship next year. And then he came back to US to Stanford University, where he received his PhD in physics in 2016, together with a PhD minor in statistics. After that, he was a Chamberlain Fellow at Berkeley Lab from 2016 to 2020, and now he is at LBNL. So we look forward to your exposition of how machine learning and quantum computing ideas are being applied to high energy physics. Over to you, Benjamin.
Thank you very much for this nice introduction and for the opportunity to talk to you about my work. So today I will tell you about modeling high energy physics radiation on a quantum computer. Unfortunately, I won't have time to say much about machine learning, but I'm very happy, of course, to talk about that sometime at the end. Yeah, so I like to start my talks about quantum computing with a quote from Feynman. I think this is very foundational in sort of thinking about the setup for what I'm going to talk about today. He says, I therefore believe it's true that with a suitable class of quantum machines, you could imitate any quantum system, including the physical world. And the physical world in this talk will be the subnuclear world. So that's the realm of high energy physics. So first, I'll tell you a little about quantum computers. I wasn't totally sure about the background of everyone here. I did a little bit of Googling around, and it seems like not everyone is a super expert in quantum computing. So I'll have a slightly pedagogical introduction, but I'll be brief. And then I'll get to how we model quantum physics in high energy physics. And then I'll provide two examples, one on final state radiation and one which is a related topic in the context of effective theory to compute soft matrix elements. And then I'll talk about mitigating noise, which is a key challenge on near-term quantum computers. And finally, I'll say a little about where this is going in the future. All right, so just to lay the foundation, the goal is to implement our system's Hamiltonian in a proxy system and let it evolve. So for high energy physics, our Hamiltonian is the standard model of particle physics. You can see it written in the Lagrangian form on this mug here from CERN. And the proxy system will be a quantum computer. And so the proxy system can be, of course, sort of anything, any quantum system, like a collection of spins. And the best quantum computer is one that looks the most like the system you're trying to model. So if you want to model a collection of spins, best to have a collection of spins. Now, in our case, we want to model high energy scattering. So here's an aerial view of the Large Hadron Collider. On the left, it's the same on the left and right, but you can see this picture of the Geneva Basin where part of the picture is in Switzerland and part of the picture is in France. And there's this circle overlaid on the ground, which shows the roughly 30-mile tunnel that corresponds to the Large Hadron Collider. And you can think of the Large Hadron Collider, where we collide these protons at very high energy, as a quantum computer. And the best way to emulate or make predictions would be to have another LHC. Take one LHC, make predictions for the other one. And while of course that would be impractical, it would also be useless because we wouldn't understand the fundamental degrees of freedom. So the idea is to implement a system, implement calculations using the fundamental degrees of freedom and make predictions for high energy scattering. So in other words, using things like a collection of spins to make predictions for high energy scattering. And in the setup, the possibilities are endless and the key is really efficiency. Okay, so I'm not going to talk about basically anything about hardware. I'm an algorithms person, but I do want to just show this one picture, which I always put on my talk because I think it's pretty fascinating. So on the left, you can see classical computers from the 1960s from IBM. On the right-hand side, you can see quantum computers from IBM now, and they're both roughly take up the size of a room and require multiple people to operate and have very little computing power. But I think there's reason to be excited about this topic in particular because of the classical trajectory we know it happened after the 60s and where we think that quantum computing is going in the future. Okay, so now I'm going to say a little bit about quantum computing in general. I suspect that many of you know about this already, but I just want to make sure everyone's on the same page. So a qubit is an abstract representation of a quantum system. It can be a superposition of two states. We often think of it as a spin. And the best quantum computers now, universal quantum computers, which are the ones I'm going to be talking about, they have sort of order 10-ish qubits, order 1 connections per qubit, and it can stay coherent for, say, roughly 1,000 operations. And picture of a quantum computer would look like the one on the bottom left, where you have some number of qubits. They have some connectivity graph, and not every qubit is connected to every other qubit. And there's a limitation in the number of operations that can be applied. And this will be relevant for the algorithms I'm going to talk about later. Okay, just like for any classical computer, on a universal quantum computer, you can write a program. Here's a very simple program. I'm going to show you some programs later that we've developed for high-energy physics. So it's important that we all get the symbology correct. So the first step is to initialize the ground state. So these 0 kets, they mean initialize, which is the first step for any program. Then you can apply operations to each qubit. So the operations have to be unitary. That's the key requirement. So this box with the U1 means apply unitary operation U1 to qubit 3. You can also do the equivalent of if statements. So these are controlled operations. The open circle means apply U2 to qubit 2 if qubit 3 is 0. And the filled circle means do it if it's 1. So apply U3 to qubit 2 if qubit 3 is 1. And of course, qubit 3 could be in a superposition of 0 and 1. And so you will apply both U2 and U3 to qubit 2, sort of in the right superposition as dictated by the state of qubit 3. You can apply multi-qubit operations. So this U4 applies a conditional 2-qubit unitary operation to qubits 1 and 2, conditioned on qubit 3. And then there's this other single qubit gate U5, but at the very end, the last thing you do, of course, is measure all the qubits. So initialize, prepare the state, measure the qubit state. And then you get a classical string. You can repeat this procedure many times and then learn something about the state you've prepared. Okay, now there are some key challenges. So not every operation is allowed on current computers because of limitations. So for instance, the most basic operations are single qubit gates. These are the squares with a single letter, and simple entangling gates. So the simplest entangling gate is this thing called the C0, controlled knot, which is the filled circle with the open circle in the cross. And there's a theorem that says that any unitary operation can be decomposed into single qubit gates and these entangling gates. Now there's no generic compiler, so a lot of this has to be done by hand, which I hear huge echo now. I don't know if that's just me. Maybe I'll keep going. Okay, it's gone now. Yeah, there's no compiler, so this often needs to be done by hand. Okay, and the other thing is that it's architecture dependent. So depending on the connectivity graph of your computer, you might have to set up your algorithm a different way because of the resources available. In particular, you can't copy or clone qubits. You can only move them, which is teleport. And so if you have, these are two different quantum computers, they have different connectivity graphs, and therefore you may have to modify your algorithm accordingly. The other thing is a key challenge is noise. So here's a plot, which I'm going to show again later. For now, it doesn't matter what the axes are. There's just some physical quantities dependence on some other physical quantity. And the point is that the TL is the output of a nominal quantum circuit. It has some trend. And then the other colors correspond to replacing every C0 operation with some odd number of C0s. And the C0 has the property that if you square it, it's the identity. And so basically by replacing every C0 with 3 C0s, for instance, you've just increased the number of operations by a lot, but you haven't changed the expected value, the true value of the circuit. However, you see that the output does change quite a bit. And that's just because basically you're injecting noise. And by injecting noise, you can see that you're amplifying the noise and you get sort of garbage. And so current computers are rather noisy, and therefore we need to minimize the number of operations that we apply. Okay, so yeah, caveats aside, there's good reason to be excited. I think I don't have to tell you that there's been impressive leaps in hardware, firmware, and algorithms in the last years. And I think that while it's unlikely it will have a quantum processing unit in our laptops 5 years from now, I think it's possible that we'll be able to make interesting calculations for science that were not possible before in the near future. Okay, so that's my whirlwind introduction of quantum computing, and now I'm going to spend the rest of the talk discussing quantum computing in the context of quantum field theory. So why is quantum field theory more challenging than other early adapters of quantum computing, like quantum chemistry? And the answer is that in quantum field theory, we have continuous degrees of freedom. So every space-time point has quantum numbers, and there's a mix of both discrete and continuous quantum numbers. So this is the field theory part of quantum field theory, is that it's a field, so everywhere there are quantum numbers. And traditionally, when making calculations in quantum field theory, there's sort of two approaches. One approach is to discretize space-time and to put it on a lattice. So this is called lattice gauge theory. And the other approach is perturbation theory. So there are some regimes where you have small couplings and you can expand the theory, and this has led to Feynman diagrams and the whole technology of perturbation theory. And there's one Feynman diagram shown on the bottom right of this slide. Now, both these approaches are effective, but they have their drawbacks. So in the lattice case, it's the full theory. It's not a perturbation series, so it includes everything. But dynamics are too hard because of computational limitations. They already use supercomputers to make progress. On the perturbation theory side, you can do high-energy dynamics, but it's an approximation, and there are combinatorial linear diagrams, and going to higher order is really cumbersome. Okay, so the quantum computers have a lot of potential to be able to make progress for high-energy scattering in the context of quantum field theory. There was some pioneering work from some years ago that showed that it's possible, in principle, to simulate the time evolution of a quantum field theory in polynomial time. Now today, I'm going to tell you about a hybrid strategy for approaching quantum field theories on a quantum computer. And in particular, I'll illustrate this with two concrete algorithms. But before that, let me sort of motivate why we need a hybrid approach and why this polynomial time construction may not be the most effective for near-term computers. Okay, so proposals for a lot of proposals for ab initio calculations on quantum computers, they use lattice methods. So basically doing lattice field theory on a quantum computer. And so you digitize the field values to make the infinite dimensional Hilbert space finite dimensional. Now let's say we digitize our fields into some number of values and have n lattice points in each of the d directions. Then your Hilbert space will be n phi to the n to the d dimensional. And on a quantum computer, the key benefit is that you only need a log number of those qubits. So that's great, nd log n phi, number of qubits. So just to be clear what I mean by that, so here you have, like, let's say some position, let's say one dimension of your field, and here's like the digitized field value. So for instance, if it's a Gaussian, like the ground state of a harmonic oscillator would be like a Gaussian, so it's like the blue, and like the first excited state would be like the creation operator applied to the vacuum. And this is for n phi equals 8. So you have basically 3 qubits in order to achieve this kind of precision. And then if you have, say, 3 dimensions, so n equals, or let's say n equals 3, so 3 lattice sites, but 1 dimension. So along that 1 dimension, you'd have say a series of say oscillators that would look kind of like this. Okay, so I just mentioned on a quantum computer we need this number of qubits, n to the d log n phi. Let's put in some numbers. So when we're putting our theory on a lattice, discretization and finite volume effects introduce cutoffs. So there's a low energy and a high energy cutoff. Sometimes call them ultraviolet and infrared cutoffs. So if the smallest lattice spacing is delta, then the approximation to the continuum theory, which is obviously the one we care about, is only good within a range of energies. So you obviously can't probe energies that correspond to frequencies higher than 1 over the lattice spacing. and then the physical size of the volume of space that you're simulating sets the range of how much the lowest energy modes you can probe. So if we want to cover, say, the relevant dynamics at the Large Hadron Collider, then we're talking about scattering where the physical scales that are relevant go from like 10 MeV, so it's mega electron volts, up to 7 TeV, tera electron volts, which is the beam energy. And so this means capital N is something like 10 to the 6. And if you plug in the numbers, right, so that's like 10 to the 18 qubits, and that's a lot more than we'll probably have in our lifetime. And so the solution that our group has been thinking about is to use perturbation theory to cover the highest energies where you need the smallest lattice spacing. And perturbation theory is very effective in this regime. And then try to find, and then basically try to use quantum computing in the other places where the computational resources are less severe. And so you can.
Sorry, Benjamin. Sorry. Yeah, I had a question on your previous slide.
Sure.
Yeah, I was confused as so you said we need order of n raised to power d log n 5 qubits. So I did not understand this point, and also why do you need order of 10 raised to power 6? This part maybe you can explain.
Right. So the n to the d. Okay, let me go back here. So yeah, basically this number is because we have for each we digitize. Okay, so we have n lattice points in each of the d directions. So we've discretized space-time. So if you have along one of the dimensions, right, you have n lattice points that represent space, and you have d of those, so you have n to the d, right?
Okay.
That's like, and then we also want to have a each lattice point would have like a continuous quantum number, so we have to digitize that because we want a finite dimensional Hilbert space. So that's why it's n phi to the n to the d. All right. And then in terms of the number of qubits, which is the log of that.
Okay, great, thanks.
Okay, and then yeah, this big number comes from the fact that if we want to span this energy range, that sort of gives us a sense for what n has to be, because if you the size of the lattice dictates sort of the smallest energies you can probe, and the smallness of the spacing of the lattice dictates the highest energies you can probe. And so the difference between the highest, so if you look at this, like this is like this corresponds to the highest energy, and this is the lowest energy, and their ratio gives you n basically. And so if you just take these two numbers, 7 TeV and 10 MeV, that gives you n basically.
Okay, great. Thanks, Ben. Yeah.
Yeah. Okay. And this is just there's 3 dimensions of space. Okay. Right. So then it's well known that the cross section for producing high energy scattering approximately factorizes into multiple components. So for probing hadronic jet physics at the LHC, which is one of the most common processes and the one that I'm most interested in, the cross section factorizes into a hard matrix element, which is this H, and then a series of other components that correspond to the collinear degrees of freedom, and then an overall soft degree of freedom. And so these J's, at least in the context of a particular effective theory, are called jet functions, but I don't want to get into that detail here. I just want to think of it as the sort of a hard component. So that's like the quarks and gluons inside the proton, they scatter, and then the outgoing quarks and gluons, they have collinear radiation, and then there's sort of a haze of soft radiation. And this hard matrix element can be computed precisely in perturbation theory, including all the quantum effects that are relevant. And so the idea is, well, let's not try to put everything on a lattice. Let's just put in the stuff that's after the H. And so in this way, we don't need to encode the full dynamics of the LHC. We can get with far fewer qubits. And the tens, hundreds, millions, or billions of qubits that may be required for some of these calculations may be possible in the not too distant future. Okay, so now for the rest of this talk, I'm going to give you 2 specific examples. So one is to attack this collinear physics, and the collinear physics is final state radiation. So you have outgoing quarks and gluons, and they radiate other quarks and gluons. And this is a complex many-body quantum system. We often call this the parton shower because we call quarks and gluons partons. So it's basically a shower of these particles. You can see schematically what the shower might look like in a picture like this, where you have some initial quark, which is the solid, which is the line, and then the squiggly lines are the gluons. The gluons can radiate more gluons. They can split to quark anti-quark pairs, and you get this shower of partons. And the idea is that many of the techniques used to simulate this kind of physics, they are classical. They're Markov chain approaches, which allow you to fill a very large phase space with very efficiently. But many of them ignore quantum degrees of freedom. And so the idea is, can we, at least the idea of this particular part of my talk will be, can we scaffold this classical Markov chain with quantum degrees of freedom? Okay. So in order to kind of get started, let's think of a parton shower like a tree. So imagine that time sort of runs from top to bottom. And so as I go from top to bottom, time is evolving. And at each step, the particle can radiate or not. And radiate will be like go left, and not radiate will be like go right. And so in this tree, there are various leaves. Leaves are at the end. And at a given leaf, you can know the history, basically. Going left means radiate. So if I go all the way left here, the particle radiated once, radiated twice on this side, and then radiated no times on the right side. And so the way this is done now is basically it's with a classical Markov chain Monte Carlo. At every step, there's an amplitude, and the amplitude for a given leaf is just the product of all the amplitudes. And in this case, you can simulate this tree very efficiently by just going left or right with probability a squared. So there's no interference effects, and you can get the probability at every leaf or at every node. Okay, so now let's add a little bit of a complication. So now suppose that the particle that's radiating has a quantum number, a discrete quantum number. So let's just think of it like a spin. So it can be, let's say, spin up or spin down. And so now, instead of having this single tree, you have something which is more like having two trees. So you have a black tree and a red tree. And in every step, you can go left, so you can radiate, or you can not radiate, go right. And or you can flip a spin or not. And so now there are, sort of being only 8 possibilities, there are 16 possibilities. And the rule is still the same. So there's at every step you have an amplitude, and a given leaf corresponds to a product of amplitudes. But now the complication is that we only get to observe the final leaf and the final color, spin. We don't get to observe intermediate spins, and there are multiple paths to get to the same leaf. And so you have to sum over those paths, and therefore there's some interference between these trees, and that sort of illustrates some of the problem we want to solve with a quantum computer. Okay, so here's an algorithm, a quantum algorithm, a quantum program that solves the interfering trees problem. So the way it works is that you have one spin qubit, and you have one qubit for each of the steps. So we discretized time into n steps, and these qubits correspond to whether there was a radiation or not, which means go left or go right. And the way it works is that basically first we rotate into a basis where the two trees don't interfere, and then basically the two trees just proceed in parallel, and then we rotate back. This rotate back, our dagger at the end. And then there are a series of these controlled single qubit gates, and basically these are these splitting amplitudes. So the controlled operations are basically controlled on which of the two rotated trees you're on. And so you can kind of think of this like you rotate and you sort of proceed in parallel where you radiate or not, and then you rotate back. And so this is a linear time algorithm that requires the number of steps plus 1 qubits to implement. So here's some histograms for running this algorithm. And so here, for instance, the left and the right correspond to, we picked one observable, which is like the number of branches. So the number of times you go left or right for some large number of discretization steps. And you can see the red, for instance, is the histogram for the classical Markov chain Monte Carlo, and the blue is for the quantum algorithm, and at least a simulation of the quantum algorithm. And you see they're different. And the right plot shows the expectation value of this number of left branches. And so you can see that when this lambda here corresponds to the rotation, the mixing between the two trees. So when the two trees are not mixed at all, the classical and quantum agree. And when the two trees are basically maximally mixed in some sense. So basically, the maximal mixing means that at every step you definitely flip trees. And so if you definitely flip trees every time, then it's deterministic. It's no longer interfering. So that's the agree again. And there's some non-trivial differences between the two in the middle. Okay. So that was a toy model, but now let me write down something more relevant for energy physics. Is there a question? I hear a lot of background noise. Okay, guess I'll just keep going. So here's a Lagrangian that corresponds to 3 particles. There's one fermion, 2 fermions, and a scalar particle. And the first one is just the kinematics, but the second line corresponds to the coupling between the particles. There's G1 that couples the scalar to the first fermion, G2 couples the scalar to the second fermion, and there's this G1,2 that mixes them. And this actually does exist, this Lagrangian in the standard model, but not in the form that we're going to use it. And so this is still, it's more realistic, but it's still a bit of a toy. And we're thinking about this in the context of final state radiation. So you have some high energy F1 or F2 particle radiating these scalar particles collinearly, and you can have diagrams that look like this. So these 2 diagrams have the same initial state, the same final state. So they interfere with each other, and there's different intermediate particles. So in this case, you have an F1 radiates a scalar, stays in F1, and here you have an F1 radiates a scalar, becomes F2, and then turns back to F1 after the second radiation. But the idea is very similar as the interfering trees, where we discretize time, and then you have a series of emissions or not. So we've developed a quantum circuit for this parton shower, and it looks like this. It's a very similar structure to the tree, where basically these are now quantum registers. So the slash means register, and we've discretized something which is like time. And at every step, you can emit or not, and these U steps correspond to the N different steps that we have to apply. So this circuit's a little bit more this algorithm is a bit more complicated than the interfering trees, in particular because you don't just have a fermion radiating scalars. You can also have the scalars split into fermion pairs, and so the number of fermions is not constant. And these registers basically keep track of all of that. So you have a particle register, a history register, an emission register, and these are auxiliary registers that keep track of the number of fermions of each type. And you see there's a number of scalars, and then these are called A and B. And they're called A and B because it's the same setup as the interfering trees problem. Is that we take the 1,2 basis, we first on every step we rotate into a new basis where the 2 fermions don't interact, so G1,2 is 0. And this is the counts in the rotated basis. And then we have to count how many particles, then we decide if there's an emission, we decide who emitted, and then we update the history and rotate back. So that's the algorithm. And this rotation matrix here, now you see it's indexed by little m. Little m corresponds to the step. And that's because the rotation matrix itself depends on time, because the couplings that we have are not constant, they run. And so this running of the coupling, it can be encoded directly into these matrices. These rotation matrices basically just depend on the couplings, the G1, G2, and G1,2. Okay, so I'm not going to go through all of the components of this algorithm, but let me just illustrate one of them to give you a sense of the complexity. So there's this step in the middle here, basically decides if there's an emission or not. And the way it works is that this is a 2x2 matrix, basically, because this is just a single qubit, this emission qubit. And it's conditioned on the number of phi A and B, number of scalars, number of fermions of type A and fermions of type B. And it looks a bit like this. And it's governed by what are called Sudakov factors. So basically what we can do in quantum field theory is we can compute what's the probability that you don't emit. And then there's these deltas. And then you have a product of these deltas. So basically we have the probability that the scalar doesn't emit, and then the 2 fermions of each type don't emit. And then basically 1 minus that gives you like the probability that there is an emission. And so that's sort of the structure of this component, which is actually the simplest component because it's only acting on a single qubit. These are the other parts they act on registers. Okay, but this encodes most of the high energy physics. Now, if we artificially turn off the scalar splitting, then you start with a given fermion. You can't make more fermions. All you can do is radiate scalars. And so now the algorithm actually significantly simplifies, and it looks a bit like this, where at every step, you just have to keep track of the spin of the fermion. You only have one fermion, you can't change it. If you start with one, you stay with one. And then you have to just keep n step other qubits that determine if a scalar was radiated at a given step or not. And then you rotate into the basis where the G12 is 0. Then you radiate or not, depending on what the state is, and then you do that n times. And you'll note that this looks just like the interfering trees algorithm. In fact, it's exactly the same. But one thing I'll note about this tree, this circuit, is that you can see that, for instance, this qubit is not touched after we apply these operations. Likewise, this last qubit is not touched until the very last two qubits are applied. And so actually, if you reuse qubits, which is now a thing that's possible on existing hardware, you actually only need two qubits. Basically, you need the spin qubit, which has to be coherent the whole time, and then one other qubit which corresponds to a given step. And then as soon as you apply this operation, those operations, you can measure it. So you can basically shift this measurement operation all the way to the left. Okay, so let me now show you some numerical results. So here are some results where we've simulated the quantum system as well as run on an IBM quantum computer. And it's for a small number of steps. So the observable that's being shown here is something like the logarithm of the maximum angle of emission. So it has this structure. And then when G12 is 0, so that's the blue, there's no interference effects. And when G12 is 1, there's interference effects. And you see that the two are different. And the blue and red triangles, those are the results on the quantum computer. And you see that they track the classical simulation of the quantum computer. The number of steps is small enough that we can do that, although of course it scales exponentially. The difference between the top plot and the bottom plot, the top one excludes this splitting, and so the algorithm is much simpler, so we can run more steps. And this is the full algorithm, so we can only run 2 steps. And even though this algorithm is it's polynomial, the naive implementation is actually a 5th order polynomial, so it actually scales a bit too poorly for us to run many steps on a near-term computer, but we're working on optimizing it, and we know ways of actually improving it to be quite a bit better. Now, the last thing I'll say about this before I move on to another topic is that the results out of the box don't look this good. We've optimized significantly how we've used the quantum computer in order to perform readout error and gate error corrections. And in the last part of my talk, I'll give you a sense for what these corrections look like and why they're important for achieving this kind of precision. Okay. I think I see a hand up.
Yeah, can I ask a question about the G12 equals to 1 case? I mean,
yes.
There is, I mean, is there something that you can compare with on the analytic side? How do you know that that result is trustworthy? Right.
So when G12 is 0, not only can we simulate it can simulate the quantum computer on a classical computer. That's the blue histogram. We can also calculate it analytically. That's this black dashed line. Then you see that the blue histogram agrees spot on with the black dashed line as it should. In the G12 equals 1 case, it's much more complicated to compute analytically. So instead, we only have the classical simulation of the quantum computer, and we have no reason to believe that should be correct. I mean, there's no noise or anything. It's just the full circuit, but we've just simulated it on a classical computer, and so that should be the right answer. Basically, the histogram value here.
And is there a reason why you could only do 0 and 1 and not say some random real value of G12?
No, we could do other values. We only wanted to. We wanted to keep the plot not too complicated. To have only 2 values. But no, we can. The algorithm scaling is the same for all values of G12, so we could have more. Yeah.
Okay. Thank you.
Yeah.
I have a question.
Sure.
You only looked at the tree level structure, but you can also have possibility of multiple interactions between the same particle which is emitted and then comes back, and then you will have loops. Does this loop effect important correction relevant to this process, or it can be ignored in the region of parameters where you are working?
Yeah, that's a good question. So in fact, some of that structure actually is already encoded in this circuit. So actually the way this algorithm works is that, so for instance, at tree level, you cannot have a fermion of type 1 not radiate a scalar and become a fermion of type 2. However, in this algorithm, that is included. Because the way the circuit works, you have a fermion of type 1 when you rotate and then rotate back, it actually does mix the two states. And so there are some higher order effects that are sort of included in this algorithm, but you're right though that that it'd be interesting to study this in greater detail, which we haven't done at the moment. All right, so perhaps I will keep going. Okay, so the second physics example I'm going to give is about soft physics. So I just told you about collinear radiation, this parton shower, and now I'm going to talk about a second type of physics, which is this soft physics. And this is another component which is difficult to compute classically. And the way that, in the context of effective field theory, in particular soft collinear effective field theory, this as is simulated, is that the soft particles really don't contribute to the dynamics of the interaction, because if you have very soft radiation, it shouldn't change the kinematics of outgoing particles. And so the way that this is often modeled is that you have basically the high energy particles. They're sort of modeled as static charges along some light-like direction. And then you have sort of these soft radiation about those static charges. And so you can see that sort of shown symbolically here, where you have some operator. Of course, there's a coupling out front G, and then there's this direction N, and then A represents the field, and there's just some direction along a light-like direction along which the field is propagating. And what I'm going to compute here is basically imagine you have the pair production of two high energy charged particles, and they're static charges, and I want to compute this soft function, which will be a certain matrix element that will correspond to basically transitions from the ground state of the theory to some final state, which could also be the ground state, which would be like there's no particles emitted, or some excited state, which would be some number of particles are emitted. Okay, and so the goal, of course, is the standard model, but the current resources are too they don't have enough to do the full problem. So let's do a simplified problem like before. So we're going to do a 1+1 dimensional massless scalar theory instead of the full gauge theory. So some complexity is lost, but some of the main features remain. Here you can see the Hamiltonian. So we have our scalar. So here should look familiar to you. Well, these are fields now. So we have we're going to have to discretize and digitize space and time. And the operators we want to apply are these are so-called Wilson line operators, which correspond to the field along some direction. And yeah, the first thing we have to do is put it on a lattice. So we discretize space, so you have some number of lattice points. And so instead of being integral over all space, there's this sum over lattice points. And you can think of it like we have a series of lattice points is 1+1 dimensions. So we could start at one of them and then sort of move the particles apart. And we also digitize the fields. So the Hamiltonian looks a bit like the harmonic oscillator. Hamiltonian, in fact, is the same. There's a natural digitization scheme where if you want to have the same precision for both the momentum and the position space operators, then that sort of dictates what the digitization should be. And I think I showed this picture earlier in the talk where you can see the ground state's a Gaussian for the scalar field theory in 1+1 dimensions, or in one dimension, and then you can see the first excited state, etc. And so here there's 3 qubits, which allows you to have eight digitized points. Okay, so here's the circuit. So we have a register of n phi qubits per lattice site, and there are some number n of lattice sites. And then the first is to prepare the ground state, which I'll say a bit more about in a second. Then we have this time-ordered product. That's the main matrix element that's shown here. And then we have the inverse state preparation, which is basically this the bra shown here that we're going to apply to compute the transition probability. And then we have the measurement at the end. So I'll just now very briefly walk you through each of these components. So the state preparation for a generic ground state requires exponential resources, which would defeat the purpose of a quantum computer. But it's known that a Gaussian state, which is the ground state of a scalar field theory, can be done with only polynomial resources. And there's an interesting paper from Kataev and Webb, which basically outline exactly how you do this with polynomial time. So this basically the way the algorithm works is that you first build uncorrelated multidimensional Gaussian state, and then you apply some shearing operations to introduce correlations. Now, we spent a lot of time studying this ground state preparation, and I can say more about it later, but basically, even though it's polynomial scaling, some parts of the algorithm, they still require a sort of large number of qubits on near-term computers. And so it may be actually better to have some kind of hybrid approach where actually part of the algorithm you allow for exponential scaling and part of it is polynomial. Because actually, in terms of the precision per lattice site, we actually don't need it to be too precise, because if you imagine your space-time, most of the points will be actually in the ground state, and so you don't really ever need to have high precision on some large excited states. But I don't want to get into that digression right now, and stay tuned for more details about that. Okay, so yeah, here's what some states look like. So for instance, if you have 3 lattice sites, this is like what the Gaussian ground state looks like, where you have sort of analytic is in gray, and then there's this approximate procedure that's polynomial scaling in orange, and then you can just generate the ground state, for instance, in Qiskit, which is a quantum computing software from IBM. And here you can see what the 3-dimensional, at least a version of the 3-dimensional for each of the 3 lattice sites looks like. Okay, so then there's the time-ordered product. So this is the main component, and it requires 3 pieces. So first we have to express the field phi in a form that we can implement on a quantum computer. So you can write the phi as a sum of sigma z operations. And then we apply some quantum Fourier transforms, because we need to have both the phi and the pi operator. So phi squared is just this operator squared, but pi squared would be the quantum Fourier transform of phi squared. That's what you see here. And then we have to do time evolution, which we can do with the trotterized time evolution, basically because pi and phi don't commute. And so if you want to do naive time evolution, basically the way to do it is to break it up into pieces of where you have the pi and the phi separately. Okay, so that was a lot very quickly, but these are sort of standard approaches for each of these components. And then comes the measurements. So I'll show some results on one of the IBM computers where we have 3 lattice sites and 2 qubits per lattice site. So with only 3 lattice sites, actually turns out the matrix element simplifies significantly. And I don't really want to get into the details of why, but basically the time evolution more or less cancels out. And so all you have are basically there's the state prep, and then we have this operator that's shown here, and then the overlap with the particular state, so the ground state or the excited state or whatever. Okay, yeah, here are just some plots that show the scaling with the number of lattice sites. So as you add more number of qubits per lattice site, obviously you need more resources. And this bottom one is the number of single qubit gates that are required, and this is the number of entangling gates that are required. And you need sort of, you need only 10-ish for the number of qubits that we're probing. Then you need, hundreds if you want to go beyond that, which is where we're going in the future, but we're not there yet. Here's the circuit itself. So these are each of the qubits. There are 6 of them. And you can see the single qubit gates. These are these red boxes, and then the entangling gates are the blue components. And then we have some number of operations in the end we measure. Actually, these middle 2 qubits, you can see that there are these C-naughts that come together. So these C-naught pairs actually can be canceled, because I told you C-naught squared is identity. So these cancel, and then there are other cancellations that actually make the algorithm on the middle 2 qubits pretty simple. And it's really only non-trivial in the first and the last pairs of qubits. Okay, here's the result. So this is the transition rate. So you can think of this like the no emission probability as a function of the coupling constant G. So when the coupling constant is 0, you never emit. So basically the overlap with the ground state is 100%. And then as you turn up the coupling constant, you start emitting more and more, and your overlap with the ground state goes down. And there are a variety of points here. So the blue is the analytic calculation that we can make in this simple theory. And then the orange is the digitized version without noise. And so the difference between the blue and the orange is just that's the result of digitization, nothing to do with quantum computing yet. And then the green is the raw output of the quantum computer, and the black circles are the corrected values using error mitigation. You can see the black circles and the orange dash agree quite well, which is really exciting. Okay, and yeah, here's just the plot that shows how things converge as you have different numbers of qubits. So as I mentioned, we have 2 qubits per lattice site, and you can see that 2 is already very close to infinity. Basically, so the blue is the analytic calculation with digitization effects. And you see that having 1 is pretty far from the right answer, but then once you have 2, which is orange, it's pretty close to the blue, and the green is spot on. Okay, the last thing I want to talk about here is that I mentioned that there's these green components is the raw result and the black is the corrected result. So how do we get from green to black? So the results are not that great out of the box, and we have to apply error mitigation. Okay, so in the last few minutes of my talk, I'll discuss error mitigation. So there are 2 kinds of errors. There's readout errors and there are gate errors. So for readout errors, the idea is that a quantum computer may the state may be in a 1, but you read it out as a 0, and or vice versa. And so if you have n qubits, the transition from the actual state to the measured state requires encoding a 2 to the n by 2 to the n matrix. And you can see on one of the IBM's computers what this matrix looks like. This is for 5 qubits. So there are 32 possible states that it could be in, and 32 states it could be measured in. And you can see that most of the diagonal is most of the results are close to the diagonal, which is good. So if you start in a state, you end in the same state. But if you look at the actual numbers, if you squint, it's sort of like 70 to 80%, which is great, but there are significant, migrations. So it actually turns out that high-energy physicists have spent a lot of time thinking about this problem. We call it measurements, measuring differential cross-sections, and we call this procedure unfolding. And so we recently had a project where we applied unfolding algorithms developed in high-energy physics for measuring differential cross-sections. So this is like bin differential cross-section measurement, applying that to readout error mitigation on a quantum computer, because basically they're exactly the same problem. This plot on the bottom right just shows some Gaussian state prepared on a quantum computer, and with some pathological migration matrix, such that if you just apply naive matrix inversion, then you get this oscillatory behavior. Whereas if you apply one of the standard procedures in high-energy physics, you see it's spot. You can't even tell the difference between the green and the black because they're really spot on each other. And so these methods we developed in high-energy physics, they circumvent known pathologies, and they may be useful for also for quantum computing. All right. So then, yeah, one last point is that we haven't stopped, so we're still actively developing protocols for improving readout errors. And so, for instance, one thing we noticed recently, well, this has been noted for a long time, but it's well known that the transitions from 1 to 0 and 0 to 1 are not the same. And so the 1 to 0 is much more likely than 0 to 1 because it takes a long time to measure a state, and so they can decay. And so, in fact, you can apply some procedures. So this is this top picture shows the standard procedure where you have some circuit, then you do some measurements, and then you apply some error mitigation. But you can actually, if you happen to know a little bit about your state, so if you know that your state has a lot of is going to produce a lot of 1s, you can apply an X gate just before you measure to turn the 1s to 0s, and then apply some classical X gate after you measure. And this way you can have as many zeros as possible, which actually can improve your readout fidelity. I see a hand up. Apurva, yeah.
I have a question.
Please.
You mentioned this HEP standard techniques to improve the readout accuracy. Can you explain what these HEP standard techniques are?
Right, there are a variety of techniques. This particular one is called iterative Bayesian unfolding, and the idea is that it's basically maximum likelihood. So it uses an expectation maximization style approach to maximize the likelihood. And one of its, so it has a few nice features. So one feature is that it's automatically non-negative definite, which is not the case if you just invert the matrix. Of course, the matrix inversion also achieves the maximum likelihood estimator, but if you just apply the matrix inversion for noisy data, right, you can get negative values. Also the way that this iterative Bayesian unfolding, the Bayesian part of iterative Bayesian unfolding, although it's not really a Bayesian algorithm, is that you start with some prior, and so if you kind of know roughly what your distribution should look like, then it has some regularization that allows you to measure things accurately given some finite data set. Yeah. I can go into more details a little bit later, but basically it's an expectation maximization algorithm to do maximum likelihood. Yeah.
Okay.
All right. So that's the last thing I want to say about readout errors. And then my last topic will be about gate errors. So basically, one of the main challenge of the quantum computer, right, is that the system should be as isolated as possible, but you still want to be able to manipulate it, and those are obviously in tension, and that results in gate errors. And so you apply some operation, but you do a little bit of what you want to do and a little bit of what you don't want to do. And one of the standards in quantum computing is what's called zero noise extrapolation, where you take your circuit and you replace, for instance, your entangling gates with some odd number of entangling gates. And as I mentioned earlier, the C0 squared is just the identity, and so this should have no effect on the result, but it systematically increases the noise, and then you could extrapolate to no noise. So this is exactly this plot I was showing you earlier, where if you replace every C0 with 3, 5, or 7 C0s, and then you can basically extrapolate at every point from using the data at 7, 5, and 3 and the nominal circuit, you can extrapolate to no noise. So we made the observation recently that actually you can promote these the n's, the number of times you replace each C0 to a random variable. So the typical thing that people did was you replace every C0 with the same number of C0s. But if you do it randomly, you can actually derive the optimal probability density for the random number, and you can achieve a much more efficient approach. So I don't have time to explain, but basically the standard approach required, if you have n C0s, then you require if you have little n C0s in your circuit, then you need capital N times little n additional gates, where capital N corresponds to let's say the precision you want to achieve. Whereas this randomization, actually, it's constant time, or constant resources. It doesn't require capital N. It only requires 1, 2, or 3, some small number of additional gates. And this picture here shows the extrapolation error for a simple circuit on the left-hand graph. So that as you correct more and more, the error goes down, which is good. But the more important is the gate count on the right. So the blue dash that's the standard approach. It requires a large number of gates, whereas this random approach requires way fewer gates to achieve a higher precision. Okay, so that's all the content I wanted to have for my talk, and I just want to give you a few parting words before I'll happily take more questions. So on the quantum field theory side, we're still pushing on new directions, so trying to extend the part-time shower model, understand different kinds of radiation, not just the simple scalar radiation I talked about, and maybe it could have phenomenological implications for certain high-energy physics processes. We're still trying to push also towards the standard model, thinking about other sources of interference, and we mentioned this effective field theory lattice approach that we recently studied. On the error mitigation side, we're still studying various types of readout error mitigation and gate error mitigation. And here's just another plot I didn't have time to discuss today, basically where we've proposed a polynomial time compiler, which is complementary to existing approaches and can reduce the number of gate counts significantly. And lastly, there are interesting ongoing work in the software-hardware interface, basically custom operations and tailored hardware. One of the topics in this area, as I very briefly mentioned earlier, is that our part-time shower algorithm, we actually know how to reduce the computational resources from n to the 5th to n to the 3rd by doing some remeasurement, which is now possible on near-term computers. So I think there's clearly a long road ahead, but I think quantum algorithms are very promising for modeling high-energy scattering. At the same time, we can use our experience in high-energy physics to contribute to quantum computing in general, which is the topic I mentioned related to error mitigation. And I should say that as you all know, probably the field is rapidly advancing, and it's been exciting to work at this interface between experiment theory, instrumentation, and computing. All right, thanks for your time.
Thank you, Benjamin. Now the colloquium is open for any questions.
Yes, I see, yeah, please go ahead.
Hi, thanks for the very nice talk. I have a very naive question. So in all of these that you're doing, for example, suppose you want to calculate a process for a given order, right? You need to know the Feynman diagrams, right? So classically, right? Or can your quantum computer, like, so say I want to do something in third order, right? Can it actually generate all the Feynman diagrams on its own and then calculate, or can it not do it?
Right. So, for instance, this last thing I talked about, the soft matrix element, it's not perturbation theory.
Yes.
So you basically are simulating the full theory. So there's no, it's to all orders. The approximation comes because you have a finite number of lattice sites and digitized points per lattice. And so just like lattice methods, there's no diagrams involved because it's not perturbation theory. So from that context, it's the full theory. Yeah.
But I'm mostly asking about the initial part where you talked about the high energy part of these things, right? Where you're focusing on
that was high energy. It's part of the full matrix element requires the soft matrix component. But yeah, for the final state shower, that is in the context of perturbation theory. Okay. And I suspect that it could be possible to systematically improve that, going to higher order, taking into account higher order effects. I mean, even at the lowest order, we're ignoring quantum effects at the moment using these classical Markov chain Monte Carlo methods. But indeed, yeah, I think we could also go to higher precision.
Okay, thank you very much. Thanks.
Yeah, I have another question. You gave two models, one for high energy shower and the other is for low energy Wilson line connections. But the full amplitude will need to connect this high energy part and the soft energy part with some intermediate steps. And that you had written in the diagram as some J1, J2, etc. How do you propose to do that?
Right. So in the context of, for instance, effective field theory, so let's say soft collinear effective field theory, then these objects are well-defined matrix elements that you can calculate separately, and then it's known how to combine them. And so if we can compute the corresponding matrix elements, so for instance, this H, this is computable in perturbation theory, and it's been computed for a variety of processes. And then if we can compute this soft matrix element, then we can combine them using the prescriptive language of effective field theory to make full calculations for the cross section.
Yeah, but you need some matching conditions, and they have to be chosen consistently with the principles of the theory.
Yeah, absolutely.
Is there a technique for that?
Yeah, indeed. Yeah, so that's a problem that's already been sort of approached. People have made calculations in this context, right? So, but you're absolutely right, and there are scales. I've suppressed all the scales, right? So there are of course scales that are hidden in all these symbols, and the scales have to be matched appropriately at the various boundary conditions of their validity. But this is something that is it's known how to do that.
Okay, Yogendra, go ahead.
Thank you, Professor Patel, for giving me this opportunity. I have a very naive question to Dr. Benjamin. As a mechanical engineer, I was just wondering whether this type of quantum computing that you described so nicely, whether it somehow biased towards an underlying theoretical concept like the standard model, or can it be used in situations where you just have a whole lot of data without having any particular theoretical framework on which you can draw any conclusions. So, regular data-driven models, as we say in engineering. So I'll be happy to hear your comments on how we could take advantage of your work and extend it to other areas of engineering. Thank you.
Yeah, so there's been so in this context, the answer is that this is in the context of positing a particular model, and then we would compare the predictions from the calculations with data.
Mm-hmm.
And we're not limited to the standard model. So this H here, for instance, it can incorporate, you could posit that there's some new particles, and they would go into there basically. You'd have some production of new particles. We could simulate it, on our quantum computer or combine with classical calculations, and then we could compare that to data to see if it looks more like the standard model or like the standard model plus new stuff. At the same time, so this is sort of theory-driven simulations. There's been some interesting work on quantum machine learning in more data-driven approaches. It's less obvious how those will lead to new insight, but I think it's still early days, and so I'm also pretty excited about what the potential is from that side as well.
Thank you, Dr. Benjamin, for a very enlightening introduction. Thank you.
Yeah, any more questions about any other topic?
Can I ask a simple-minded question? So when you ran your simulations in the IBM Cube, is that what you use, IBM Cube?
Yes.
What kind of runtime did you need? I mean, what kind of resources, or how many hours did you need to run the simulation?
Yeah, the simulation itself runs almost instantly, right? So the coherence times are like hundreds of milliseconds. And so from that perspective, we required very little resources. You spend more time in the queue than you spend actually running. So for these algorithms, the requirements are sort of like 5 to 10 qubits, 10 to 50, entangling gates. That's sort of the regime we're in right now. We're of course trying to push that, but the actual time is very little basically, because the quantum systems can't be coherent for very long, so you don't have that much time to perform operations. Yeah, but it's pretty amazing. Like the way it works right now is like I write the code, I compile it or transpile it for the computer, and then I submit a job basically to a quantum computer, and I get back some bit strings, and then I interpret them. So it's really like feels like almost like interacting with any other batch system. Basically, it's like a quantum batch system. So it's pretty impressive that that's now from the hardware side that's now a thing that's possible.
And in the case where you could also run the classical simulation, maybe using classical algorithm, how much time would that have taken on a classical computer? I mean, can you compare meaningfully? Yeah,
that's a good question. Yeah, so I did show, for instance, any of the examples, but let me just go to this one, for instance. Like there's this, well, not this one. Oh yeah, let's say the orange line here. What we did is we have a classical simulation of the quantum computer. So that obviously scales exponentially. And so the quantum calculation, it takes milliseconds or less. And the classical calculation, on my laptop, it takes minutes or less, but roughly minutes. So I mean, this is only for 3 lattice sites, but if I can tell you that if I go to 4 lattice sites, or instead of 2 qubits, 3 or 4 qubits, then I can't run it on my computer. It takes forever. Thanks. So we're not far from reaching a point where it very quickly becomes more inefficient to run this classically. Yeah.
Right. Thank you.
Hey, so you talked about what? Am I audible?
I hear you. Yes, please.
Yeah. Your voice broke off in the middle.
What? I didn't hear. Okay. Yeah. So you talked about quantum compilers. So at what stage are we on those quantum compilers? And how means so we currently have some basic operations. So what would our compiler look like? So in terms means I wanted to get a understanding over that. How are we doing that?
Right, there's a lot of work going into compilers. It's a very hot topic right now. One of the challenges is that it's very architecture dependent. So there are a variety of different quantum computers that don't even use the same basic principles, right? Like there's like superconducting qubits, or there's like ion traps, and so just requires totally different, and also different connectivity and all that kind of stuff. So but there's been amazing progress, basically trying to translate. There are algorithms that identify patterns that translate your algorithm into whatever gate set a particular computer has. I'm not sure if that's the answer to your question, but there's no like universal standard one that everyone uses, and they're still all rapidly evolving. Basically, as new computers come online, they have to modify their algorithms and their different approaches to try to make the procedures more efficient.
So currently, is it like what I wanted to understand is so in a normal CPUs, are we on the stage of like, so when you say gates, I understand this, that gates are at the hardware level, and we have basically some registers or means some instruction set we have, and we just program those instructions. So basically gates are hardware, hardwired into the chip basically. So similarly in the quantum chip you will have quantum gates hardwired, and we'll have some memory bits which will take the values and program them. So when you say gates exactly, means I sort of confused there.
Right. So the thing that one needs to do is translate. So then we go back to that. Yeah, you have to translate your algorithm. I think I was talking about that. Yeah, here for instance. So like, let's say your algorithm has this operation. So most computers don't have a generic single qubit controlled gate. Like they're just not in the gate set. So a given quantum computer will have a small number of operations you can apply on each qubit. And so you have to decompose this operation into these operations, because every computer has single qubit gates, and yeah, I hear a lot of noise. But basically, these gates, they have some parameters. So for instance, this Lucina gate has no parameters, but the single qubit gates, you can think of them like rotations, right? So there's like an angle. And so you have to either decompose into whatever angles are allowed, or you have a continuous angle allowed. You have to basically program that angle.
Okay, I get it.
Okay, any more questions? It looks like there are no more questions. So let's thank Benjamin for a very nice talk and interesting applications about real world toy models, but for possibility of extending them to real world. And this kind of examples keep the interest in the field alive. Thank you very much, Benjamin.
Thanks, Ben.
Yeah, thank you for the opportunity. Take care, everyone.
Bye.
Thank you.